right? And so if your past teacher said to do it this way, and I say to do it in a different way, you should make an effort to do it a different way, because I'm the one. I mean, if the past teacher is giving out the grades, then no problem, but I'm giving out the grades. And so I'll try to conform to what I ask. Like, also, with the driving force, maybe this is a point of confusion. And the driving force is, all you really need is one driving force, right? That's it. But if you know more and you can say more, then do it. Say more, show it. So what we're going to do is we're going to just look at some nomenclature problems. So this one was complicated, and at least I wanted some word about why this one, but could have been potentially complicated, but it wasn't in the end. Sorry, we'll get started here. You can come after class. All right, so we're just going to continue with nomenclature and look at some examples from the homework. Chapter 24. Let's name some of these here. So the first one is going to be this one. It's a CONH36 2+. How do you name that? You name the metal first or the ligands first? Ligands are always named first. It's backwards. And so 6 is how many? Hexa, and then what do we call NH3? We don't call it ammonia, we call it amine with 1M or 2M? Yeah, this is a 2M amine. So hexamine, all one word. And you could use double dot, hexamine, no space. And then we put the metal, and there's no space there. Normally we put a space between the metal and whatever else, but in this case there's no space. It's just going to be that's cobalt, right? And so is that going to be cobalt or cobaltate? So this is hexamine with 2 M's, and cobalt, no space. 8 or just cobalt? Cobaltate or cobalt?
Cobalt.
Just cobalt. And how did you figure that out?
Because yesterday you were saying that the metals, you don't change their names at the end, if they're at the end.
Not exactly. That's not the reason why. Did somebody else know when we use cobalt and when we use cobaltate? And when we use it, it depends on the net charge of the complex. If the net charge is positive or neutral, we leave the metal name alone. Only when the net charge is negative, that is anion complexes, only for anion complexes, we change the name. It's like an anion. If you have chlorine as an anion, you call it chloride, right? But the same thing for these complexes. We change it, the ending, just to make it. And so this would be hexamine, 2 M's, cobalt, because it's not an anion. And then what's the charge on cobalt? 2. And so it would be Roman numeral 2. There's no spaces. This is all one word, right? This would be the cation, so we could call it an ion if we want. This part is not necessary because, you know, based on the name, it's gotta be an ion. And so hexamine cobalt 2 is the name. What's the next one? B, 2B. Okay, the metal or the ligand first? Ligand, and the ligand is fluoride, but we change the ending. When fluoride is a ligand, we call it fluoro. We just add the O ending. And so this will be, we have 6 of them, so again, it'll be hexa, fluoro, and then we have a choice, aluminum or aluminate. Aluminate. The reason it's aluminate is because why? Yeah, it's an anion complex. So we know we have an anion complex when we see the metal that ends in E. Aluminate. What's the charge on aluminum? 3 plus or 3 minus? The charge on aluminum is going to be 3 plus because it's 6 times, fluoride's minus 1, so 6 times minus 1 is minus 6. Minus 6 plus what gives us minus 3? So it's going to be plus 3. And so this is going to be aluminate, and then we indicate the oxidation state of the metal, that is the charge on the metal, with Roman numeral, plus, that would be plus 3 charge on aluminum here. All right, let's go to 2C. What's 2C? Okay, what is this ligand called? Because we do the ligand first, right? Cyanide, and so it's not cyanide. It should be cyanido or cyano, which sounds more cyano. This would be cyano sounds better. And so this is going to be 4 is what? Tetra. Or tetrakis. You know, there are 2 ways of saying 4, tetra or tetrakis. Which one should we use, tetra or tetrakis? Tetra. The reason we use tetra rather than tetrakis is because cyanide or cyano does not contain di, tri, or any other prefix in its name. So this would be tetra, and then space or no space? No space. And then cyano. Okay, copper or copperate? Copperate, but you know, copperate doesn't sound good. It sounds off a little bit. And so rather than saying copperate, they call it cuprate. So this would be tetracyanocuprate. There are other metals that we change to the whatever Latin name for. So those usually from the symbols you can see. So for example, tin, you know, tin, would it be tinate or stanate? Stanate. Lead, would it be leadate or plumbate? Plumbate for lead. Silver, would it be silverate or argentate? Argentate. Gold, would it be goldate or orate? Orate. And so some of these we're going to use the origin name. And so this is going to be cuprate. What's the charge on copper? +2 or -2 or what? +2. So it gets Roman numeral 2. All right, now we have 2 different kinds of ligands on this one. And so there's a choice, which one we name first. Which one we name first, it goes alphabetical. And so alphabetical by name, let's do it that way. So this is bromide or bromo as a ligand. This is amine, therefore amine comes first. Well, if amine is named first, why didn't they write it first? You know, this seems to make sense to put it in alphabetical order here too, but the organization is a little different. The organization in the formula is they put all the anion ligands first, followed by the neutral ligands. All the anion ligands, if there are multiples of those would be alphabetical, and then the neutral ligands would be. And so they separate it from the charged ligands and the uncharged ligands, and then organize it based on that. Whereas when we name it, we don't factor that in. We're just going to name it according to the alphabetical order here. And so what would the name of that be here? Tetraamine. Tetraamine, almost spelled it with one M. If I spelled amine with one M, what am I talking about? Yeah, the organic bases, weak bases, nitrogen base. Tetraamine. Well, we have two bromos, so we have two, we could call it di, or we could call it bis. We would call it di. We call it dibromo. We wouldn't use bis. The only time we use bis, let me tell you the only time we use bis. The only time we use bis is if we have like ethylene diamine, you know? Did I talked about this, right? No? So if I had two ethylene diamine, should I call it diethylene? Diamine? Or should I call it bis-ethylene? Diamine. The second one, I'm going to call it the second one because this one appears to have two ethylenes and two amines. If you're talking to somebody, you wouldn't say, oh, that's amine with one M, or that's an amine with two M's. You just say diamine, right? Diamine is two ammonias. And so automatically you might think you have two ethylene molecules and two amine molecules. Is that what you have? You don't have two ethylene molecules and two amine molecules. Instead you have two ethylene diamine molecules. Does that make sense? And so we could even put parentheses around that to emphasize that this is two ethylene diamine. And so this is what we call a name. When di occurs in the name, or tri occurs in the name, you aren't going to find tri occurring in the name, but when di occurs, well, you could have a triamine. And sometimes I'll get fancy and put something. Okay. Okay, so we're going to use dibromo, and then is it going to be chromium or chromate? It's going to be chromium. And what is the charge on chromium? Well, the charge is, amines are neutral. Bromide is -1, so -1 times 2 is -2. -2 plus what equals +1? -2 plus x equals +1. X must be 3. +3. That would be it. These are all ions. Some cations, some anions. Let's name this ligand. What's H2O named as ligand? Water is called aqua. What's methylamine named as ligand? It's just called methylamine. We don't change the name. We only change the name for which molecules? Aqua, amine, nitrosyl, and carbonyl. All right, let's name some of these other species here. Okay, let's go with 7A. What's this called? Tetrachloroplatinum or platinate? Platinate. So tetrachloroplatinate, but what's the charge on platinum? is it -2?
The 2 plus.
Oh, it's 2 plus, you're right. So this -4 plus 2 gives us -2, so it'd be Roman numeral 2. All one word, tetrachloroplatinum 2. Okay, this little prefix here, FAC, tells us about the structure. This is a facial isomer. So we can ignore this, but sometimes you'd include it in the name, the facial form of this. Now, okay, we have more than one ligand, so what we do is we name them alphabetically regardless of charge. So, which one goes first, the aqua or the amine? Amine. So, tri, amine, tri, aqua, no space. Trimene, triaqua, cobalt or cobaltate? Cobalt. Now, what's the charge on cobalt? +2. This cobalt here, you can see, this cobalt would be 6 coordinate, this would be octahedral complex. This is a 4 coordinate. Now you don't have to know this, but later on you'll start to see it. The platinum 4 coordinate complexes are usually square planar or tetrahedral. Square planar or tetrahedral. Well, so platinum actually turns out it's usually square planar. We talked about yesterday. But that's just, these are experimental observations. How can you predict it? It's very difficult to predict, unless you need more theory, of course. But right now we haven't introduced any theory, have we, in bonding. Later on we'll talk about the theory of the bonding in these. Well, let's go on to this next complex. How would you name this one? Okay, chloro or aqua, which one comes first? Aqua, this would be tetra, aqua, chloro, chromium or chromate? Chromium. And the charge on chromium? Not +2, +3 because of the chloro. Chloro is -1. +3 minus 1 gives us +2. Sometimes we use abbreviation. Oxalate is C2O4, but oxalate's a very common ligand. Oxalate's somewhat hazardous because, if you consume it, it's not generally regarded as safe because oxalate is what we call a chelating agent. A chelating agent is a bidentate or higher ligand. Now, why bidentate? Chelating comes from claw, and the reason why bidentate ligands are chelating agents and higher is because you have to break both bonds simultaneously to knock it off. Because if you knock off one end, the other end's still attached, and then you try to knock off this end, but the other end can reattach. So we have this effect, and so that makes it difficult. And so these being chelating agents, is this a linear, coordination number 2? No, actually this is square planar. This is a coordination number 4 because we have 2 bidentate ligands attached to it, this. And so there's actually 4 atoms bonded to platinum, but there are only 2 molecules bonded to platinum. Now, the coordination number is how many atoms are bonded to platinum, and in this case, the coordination number would be 4. Does that make sense? Because these are bidentate ligands. Yes, sir? Do you need to see the structure? We said that oxalate is a bidentate ligand. Why is it not more? Because, oxalate should be a tetradentate ligand, it looks like, at least. So it's bidentate because of the, these are trigonal planar, and so if this one binds, these 2 oxygens are on the opposite side of the molecule, right? There's no way these can bind. So this can bind to platinum 2 here. Well, if the platinum 2 is here, and so this comes in here, this comes in here, bonds here. And we have another one that can come in here. And so we call this one what? Well, the ligand is oxalate, but, you know, it's an anion, so change the name to oxalato or oxalato. Oxalato is the name of this. We have two of them. So how should we name them? Your book does something funny. The way they draw complexes, I don't necessarily like, because, you know, when we have a line here like this, a line representing a bond represents how many electrons here? 2. And then your book retains the lone pair. And so it's kind of, it's weird, you know, to have a lone pair and a line. So, you know, when I draw something like this molecule, which we'd call, what would we call this molecule? We have these two oxalate ions bonded, C2O4 2 minuses. Remember that we don't do anything with formal charge. And so platinum stays as what? 2 plus. And then oxalate stays, you know, this should not be negative here. You know, this is an oxygen with 2 bonds and 2 lone pairs. An oxygen with 2 bonds and 2 lone pairs should have a formal charge of 0, right, like in water. But, you know, we do something funny. We just ignore the changes in formal charges, and we just call it as it was before it reacted. And so oxalate is still 2 minus. Platinum is still 2 plus. And so how do we name this molecule here? Di or bis? Di or bis? Di, because oxalate does not contain a prefix in the name. So it would be di, oxalato, platinum or platinate? Platinate. And what's the charge on platinate? Dioxalato, platinate. -2 plus 2 plus 4, what's the charge? Plus 2 would be mole 1 and mole 2. Yeah. Dioxalato platinate. That was dioxalato. That's a square plane. This one is actually an octahedral complex because we add another oxalate ligand on there, then the coordination number goes up to 6. Well, I'm not going to test you on structure. We just want to name these things. So what is the name for this one? Trioxalato, chromate, the charge on chromate? 3 plus, yeah, the charge, so it would be Roman numeral 3. So trioxalato chromate 3 will be the name of that anion. Chromate, you know, there's a bit of confusion because a lot of people think chromate, CrO4 2 minus. You know, they memorize in Chem 1A, Chem 4, chromate, CrO4 2 minus. But this chromate's totally different. You know, this chromate is not CrO4 2 minus. This is chromium occurring in an anion complex. All right, let's go to HC here. How would we name HC? Well, this is the abbreviation for ethylene diamine tetraacetate. And so we would call this, we'd have to spell it out, you know. In other words, in the name, can we just say dioxplatinate? No, we don't say dioxplatinate. We spell out the whole name, dioxplatinate. We'd like to just say EDTA, but we have to spell it out. EDTA is what? An ethylene with 2 amines and then 4 acetates. So this is ethylene diamine, like we saw earlier, tetraacetate. So ethylene diamine tetraacetate. If there's 4 acetates, each acetate's -1, so this whole thing carries what charge? Ethylene diamine is neutral. So 4 acetates would carry each one carrying a -1 charge. The whole thing's -4. 4. And so this is -4 anion. It's called ethylene diamine tetraacetate, but we changed the name to ethylene diamine tetraacetato because it's a ligand. As a free ion, it's acetate. And so acetato, iron or ironate? Iron or ironate? Actually, neither of those sound good. What do you call it? Ferrate. And so this would be ethylene diamine tetraacetato ferrate, and the charge on iron would be it's got to be 2. It's got to be +2. So ethylene diamine tetraacetato, Roman numeral 2. So do you want me to spell that out, or can you figure that out? Well, ethylene diamine is the same as we saw before. And so we'll just have our ethylene diamine. Oh, diamines with 1 M or 2 M? 2? You sure about that? 2 M's or 1 M? Well, if you're sure, I'll probably write it down. What is it? It's got to be 1 M, you know. It's got to be 1 M because it's not ammonia, it's amine. Actually, this is not, once you know ethylene, then you attach 2 amines to it. Except rather than having hydrogens bonded to it, we're going to have 2 acetates bonded to it. And so you have to go CH3COO minus here. I mean CH2, because now we're going to bond to nitrogen. So it'll be CH2COO minus. What is it? And so if you know the parts, then you can just add up the parts to come up with the whole. So ethylene diamine tetraacetato ferrate, Roman numeral 2 ion. It's a long name. All right, let's name some more. Here. I missed these three. All right, let's take a look at this here. Go ahead and name this one. Trioxalate. Okay. Trioxalate or trioxalato? Yeah, this is going to be trioxalato. Cobalt, is that right? Trioxalato cobalt or cobaltate? Yeah, trioxalato cobaltate and the charge on cobalt +2. So this would be cobaltate 2. So trioxalato cobaltate 2. S2O3 2 minus. You've heard of S2O3 2 minus? S2O3 2 minus is called thiosulfate. So if thiosulfate's the ion, then the ligand's name would be thiosulfato. And so what would this be? Would it be dithiosulfato or bis-thiosulfato? Well, thio is not a prefix, so what we could do is we could call it di-thiosulfate. Thio, do you know what thio means? Sulfur. Thio means sulfur. And all it is a sulfate replacing one of the oxygens with a sulfur instead. And so di-thiosulfato, silver, silverate, or argentate? Argentate. And the charge? On silver? +1, so it'd be argentate Roman numeral 1. So di-thiosulfato argentate. 1. All right, how about the 3A? So let's figure out. We got cobalt. We got, what's this called? OH as a ligand. OH as a ligand is called hydroxo. Then we have an aqua and amine. So which one is named first? Amine. Right? Amine. So how many amines do we have? 1, so we call it amine. We don't have to use a mono prefix. We'll just call it amine. Amine, and then tetra, hydroxo, cobalt, 3, Roman numeral 3. That's good. All right, note something here. The way that this is organized, we have one anion ligand. So anion ligands are usually written first in the formula, followed by the neutral ligands. We have 2 neutral ligands. We have aqua and amine. And so if we have aqua and amine, which one should be written first in alphabetical order? Aqua or amine? Q versus M. It comes first. M. And so, why did they write aqua before amine? Because they're getting really convoluted here, you know, and the nomenclature rules can be convoluted depending on the personalities of the people, you know, making the, or the noisiest person on the nomenclature committee, right? Always wants to get their way. But this is ridiculous to me. You know, for me, I would have put the amine before the aqua because amine comes before aqua, right? But whoever was on the rules committee wanted to do these alphabetically according to the first element in the formula. But you know, the first element in the formula is inconsistent. You know, so for example, if you have if you have, let's say, a carbon, okay, a carbon, hydrogen, oxygen, or carbon, nitrogen, oxygen containing compound, you know, what is the sequence of elements that you write? So you have 2 carbon compounds, and let's say one is, let's say, CHO, sometimes you write that, you know, or sometimes we would write it like CO, you know, it depends on the circumstances and what we're looking at. Or sometimes we don't even bother with that, because if this is an acid, we write HCO, right? XYZ. Do you see? There's inconsistencies about which element you write first. We see variations in the elements that we write first, and so sometimes we'll write NH3 like this. Sometimes we'll write NH3 like this, H3N. You know, I was trying to find ammonia and from a European chemical supply place, and I couldn't find it. I couldn't find it until. Oh, this is because I was looking for ammonia. I wasn't looking for hydrogen nitride, you know, or nitrogen trihydride. You know, I forgot which one it was. It was either hydrogen nitride or nitrogen trihydride. That's the way they named ammonia. But anyway, that's what we're stuck with. And so we're stuck with this thing, you know, here. And so NO2, do you write NO2 like this, ONO, or do you write it NO2? NO2 usually. So my preference is just to put them in alphabetical order according to their name. But you have to keep in mind, you know, that the book will put it in alphabetical order according to the formula, if there's more than one. All right, let's go on to this one here. This one is a little bit more complicated because we have ONO. Do you know the difference between ONO and NO2? Let's see, how many electrons does this have? 6, 12, 17. Two, 4, 6, 8, 10, 12, 14, 16, 17. Okay, this is nitrogen dioxide, but it's nitride ion. It's going to look like that. Well, nitride ion has two potential donors. You know, it could be an oxygen donor, or it could be a nitrogen donor. And so if it's an oxygen donor, we write the formula like this, ONO, and we call it nitrite. Let me make sure. It could be called nitro or nitrite. But what is it? Does somebody know? Is it nitro? Okay. You can see it. So if the nitrite ion links with the oxygen, it looks like this. So we write the formula ONO, and we name it this, nitrito. It turns out it's nitrito with a hyphen, O hyphen. And so we call this nitrito hyphen O hyphen. Nitrito O is how it's pronounced. If it links with the nitrogen, so it looks like NO2, then that's up here. You know, it's the same thing, nitrite, but now it's bonding with the nitrogen to the cobalt. And we're going to write the formula different. We write the formula NO2, it's the same species. It's now written NO2. And we call it nitrito N. And so this will be nitrito N. There are other ligands that do this, that have multiple donor atoms, but only one donor can attach at a time. These are monodentate ligands. And what are some of these other ones? There's one called thiocyanate. Thiocyanate can bond either the nitrogen or the sulfur. So we have thiocyanate N and thiocyanate S, etc. And so these are versatile in that sense, that they can bond either. All right, let's go back to the exercises here. And then, number C. All right, let's go alphabetical. Amine, and we call this nitrito O, right? And so this would be triamine, trinitrito O. So let's go ahead and write that out. Triamine, trinitrito hyphen O hyphen. All of them work. And then the metal, which would be cobalt or cobaltate? Cobalt. This is a neutral complex. Complexes can also be neutral molecule. And this would be a neutral molecule. Cobalt. And the charge would be 3. Or plus 3. It's a molecule, not an ion. That's a molecule, molecular compound. 3C is an ionic compound, but this ionic compound is a complex cation and a complex anion. And so we have to name the cation first and then name the anion. Let's take a look at the cation name. Cation name is, tetra platinum. Platinum occurs as platinum 2 and platinum 4. Which one is it? Platinum 2 or platinum 4? And then this one here is hexa chloro platinate. Platinate 2 or platinate 4? One would be here. Could they both be 2? So this is platinum 2, and then this is the platinum 2. That work out? They both can't be 2. If this were 2, then, and this were 2, this would be a -4. We need 2 of these cations. Okay. Could this one be 4 and this one be 2? Yes. This could be platinum 4, so it could be tetra-aqua platinum 4, hexachloroplatinate 2. And that would be +4 cation, -4 anion, and balances out 1 to 1, right? Ratio. And so it could be +4, and +2, that works out. But you have to know a little bit of factual observations here. You remember that table? From way back here. The table. You know what table I'm talking about?
Yeah, it's 24-1. I think you're right there.
24-1. Platinum 2 usually occurs as 4 and 6, or just 4. Platinum 2 usually occurs as 4. Platinum 4 usually occurs as 6 coordinate. And so I have it backwards. If I have it backwards, that's because just remember the table. Otherwise, would have worked out. This has got to be platinum 2. Why? Because this is 4 coordinate. This has got to be platinum 4 because it's 6 coordinate. And so here, this works out because this would be platinum 2. There'll be 2 plus. If this was +4, +4 minus 6 gives us -2. +2 minus 2 cancel each other out 1 to 1. Right? And so the name of this is, we named the cation first, followed by the anion. And so the cation is going to be this. Cation is going to be tetra-aqua, platinum 2, space, hexa, chloro, platinate 4. So this would just be the compound name here. Ionic compound. This is held together by an ionic bond. Okay, let's go on to this one here. This would be aqua or oxalato goes first? Aqua, so diaqua, dioxalato, ferrate, ferrate 1. Yeah, that's an unusual charge, huh? This is -4 plus 1 gives us -1. Wait, no, it can't be it can't be plus 1. It has to be, this is -4 because each of these is -2. -2 times 2 is -4. -4 plus what gives us -1? It's got to be 3. This must be plus 3. And so it's going to be ferrate 3. All right, let's name this next one. Oh, boy. This one's just normal cation. What do we name this cation? Silver or silver 1? It's called just silver because silver only forms 1 charge. It's plus 1, so it's charge. So we call it silver. Do we have to call it disilver? Should I call it disilver? No, I mean this is like if I ask you for some sodium sulfate, would you call it disodium sulfate, or would you just call it sodium sulfate? This is call it sodium sulfate, so this is the same thing. We have 2 plus 1 cation, you know. Silver sulfate's the exact same. Silver sulfate would be Ag2. The only difference is SO4. The only difference is we don't have a normal anion. We have a funny looking anion. What's the anion's name? Tetra, iodo, mercury or mercurate? Mercurate. And the charge? This whole thing has to be -2 because this is plus 2 over here, so it's got to be mercurate 2. And so to name this, it would just be silver is the cation name, and then tetra, iodo, mercurate, Roman numeral 2. That would be the name of that compound. Yeah. Let's do 2 more. Or actually, these won't take very long. Let's just do something like 12A. Can you tell what a common ligand is? Tell me what the most common ligand is. Amine. Amine is extremely common ligand. Ammonia, you know, aqueous ammonia is cheap, plentiful, and it likes to bond. Amines are good Lewis bases. And so what is this called? Yeah, hydroxyl. Chromium charge? 3. Chromium 3. 3 minus 1 gives us plus 2. All right, this one. Trimene aqua. Dichlorum. Chromium 3. This one.
What does the N stand for?
EN stands for ethylene diamine. It's abbreviation for ethylene diamine. But we can't call it EN in the name. We have to name the whole thing. Which one would we do, dichloro or diethylene diamine? Is it diethylene diamine?
Yeah.
No, it'd be this. In this case here, It's chloro versus ethylene diamine. Which one gets named first, chloro or ethylene diamine? No, C before E, right? And so chloro would come first, so it'd be called dichloro, and then bis-ethylene diamine. It's bis-ethylene diamine because ethylene diamine contains di within the name, so we can't use that series of prefixes. We have to use the other one.
So you don't consider the prefix, the bis doesn't come before the.
No, the prefix to this, no. We don't consider that in alphabetizing. We just consider the root or the base name of that. And so it'd be ethylene diamine versus chloro, no matter how many we have. And so dichloro, bis-ethylene diamine, chromium, what? Three? Yes. Sometimes we'll put parentheses around this, so it's two of these whole things, to make it clear. Bis-ethylene diamine, chromium, 3. How about this one, 12D? How would you name that?
Tetra. No.
That's right.
Is it tetrachlor?
Yeah, tetrachloro.
Dichloro.
Tetrachloro,
Ethylene.
not best because we only have one.
Ethylene diamine.
So tetrachloro,
Ethylene diamine.
ethylene diamine, chromate, correct. Tetrachloroethylene diamine chromate, yeah, 3, Roman numeral 3. It's plus 2 chart. Okay. Well, here's one. Well, let's use a new prefix here. Let's name the cation here. What's the cation? Would this be triethylene diamine or tris-ethylene diamine? This would be tris. Tris-ethylene diamine, cobalt. Oh, what's the charge? What are the common charges of cobalt? +2 and +3. Cobalt +2 or +3. Well, if it's +2, then, okay, that would make this whole thing +2. And then the anion, what would this be? Tris or tri-oxalato? Trioxalato, we've named this one before. Trioxalato, chromate. Okay, well, if this one were +2, let's say this is +2 or +3, this would be +2 minus 6. +2 minus 6 is -4. This would be -4. -4 is kind of high. Probably +3. It's not -4, can't happen. But so this is +3. This is +3. This would be -3, and then this could be +3. And that works out. So both Roman numeral 3s. All right, are you okay with writing formulas? Or names, actually writing names. Let's go to writing formulas. Now writing formulas, okay, you notice the space here. So this has got to just be regular potassium ion. So let's go ahead and start writing some formulas here. Like potassium, well this is potassium hexacyanoferrate 3. And so potassium ions are what, K+? Now we've got to think, what is the hexacyanoferrate ion? And so we write these square brackets, right? And what comes first? The ligands or the metal? No, the metal comes first, right? In the formula. The metal comes first, and so it's opposite. And then the ligands. The ligands are going to be in alphabetical order. Well, the ligands are like this. Which one comes first, the anion ligands or the cation ligands?
Yeah.
Anion ligands. So first, anion ligands alphabetically. But not alphabetically according to name or alphabetically according to formula? Okay, when we name these things, we do it alphabetically according to name. When we write the formula, we do it alphabetically according to formula. Can you believe that? Why? It's ridiculous, but that's the way it is. Right? And so they make it more confusing and complex than it should be. They should just do it alphabetically according to name. That'd be easier.
So the other way is the cation and the anion, so the formula is the anion, the ligand, so the anion.
Yeah, right. That kind of thinking. Right.
Okay, all right.
And so alphabetical, you know what? I don't really care. If you do it alphabetical according to name, that's fine. Right? It's alphabetical. 2. And you know what? You see, because if you are in, as a chemist, you'll see the nomenclature rules change depending on the personalities of the committee. And so if you go back to Petrucci, we're on the 11th edition. If you go back to Petrucci 8th edition, it was the neutral ligands first, followed by the anion ligands. And then the 9th edition, they switch it. It's the anion ligands first, followed by the neutral ligands. And so what you see in practice is when you go grab a bottle of reagent off the shelf, you'll see a whole variety of names. So you got to get accustomed. So hopefully we just stick with one pattern and then just do it. And so then it's going to be neutral. So second, we do neutral, alphabetical. And we'll just do it alphabetical according to name. So everything's alphabetical according to name. And if it's backwards from what they have up here, like for example, over here they write aqua before amine. If you write amine before aqua, that's fine. I'm not going to deduct anything for that. But I will deduct for other violations in nomenclature rules that I think are more important. And so here we have iron, and then what's our ligand? Cyano. What is cyano? CN. And so we have 6 CN. Cyanide is -1 charge, -6. Iron is +3. So -6 + 3 gives us -3. And then we put it together. How many potassiums do we need to balance this charge? We need 3 potassiums to balance out that charge, and the formula is going to be K3FeCN6 potassium hexacyanoferrate. All right, let's do the next one. 4B would be bis-ethylene diamine copper 2 ion. So bis-ethylene diamine copper 2 ion. So it's complex ion, square bracket. What comes first? The copper. The metal comes first. And so the metal comes first. In the formula, metal first. In the name, metal last. People get that confused all the time. Okay, next what? We have copper. And then what? Okay, 2 ethylene diamines. Now you're saved here, because do you know the formula for ethylene diamine? EN. You don't have to have the whole formula memorized. But, you know, this is the problem. How should you write the formula for EN? Should you write it as a condensed structural formula? You know, because as a condensed structural formula, it would be H2N, CH2, CH2, NH2. So does it begin with an H, or should you write it like organic formula? C2N2H2, 4, 6, 8. So does it begin with hydrogen, or does it begin with carbon? You know? Or how should you write it? So this is why, if there's more consistency in how we wrote formulas, then I wouldn't I would care. But, there's no. And so, anyway, we'll just write this EN, or do we write it E? Which one is it alphabetized? These are all ethylene diamines, so should we alphabetize it according to H, according to C, or according to E? You know how Petrucci does it? He does it according to E, not because of the name ethylene diamine, because of the formula E. Can you believe that? But anyway, he's following other people's rules, so I can't blame him. But anyway, so we're going to keep it simple, just alphabetical, however you want. So C-U-E-N, how many of these do we have? 2. And then that's it. And what's the charge on the ethylene diamine is a neutral. Copper is 2, and so this whole thing is going to be 2 plus. This is going to be a 4 coordinate, actually not, because these are bidentate ligands. And this is actually 4 coordinate copper. Copper can also be 6 coordinate. Okay, let's go on to 4C. Penta aqua hydroxo aluminum 3 chloride. Okay. Penta aqua hydroxo. Do you see the space here? The space indicates that this must be the cation here. This must be the anion. So the anion is simple. The anion is just chloride ion. So we can write that here at the end. We've got chloride. But the cation is a complex one. And so what is the complex cation here? Complex cation is going to be penta aqua hydroxo aluminum. What do I write first? The metal, aluminum, Al. And then I have to write the anion ligands first. Do I have any anion ligands? Hydroxo. And so AlOH. And then I write the neutrals in alphabetical. Well, I only have one neutral. It's aqua. And I have 5 of those. And so this would be penta aqua hydroxo aluminate, or no, aluminum. Well, the charge on aluminum is 3 plus. So this is plus 3. Hydroxo is minus 1. And so this little thing is going to be 2 plus. How many chlorides am I going to need? I'm going to need 2 chlorides to balance out that charge, right? And so when I add these up, I'm going to get this formula. It's just going to be AlOH, H2O, 5, Cl2. So this would be, penta aqua hydroxo aluminum 3 cation with a chloride anion. D. Indeed, this is another ionic compound, and you can see the cation comes first. Very long name for cation. Space anion. What's the anion? Sulfate. So the anion sulfate is pretty simple. That's just SO4 2 minus. But the cation is going to be more complex. So let's look at the cation here. Amine chlorobisethylene diamine chromium 3. So what comes first here? The metal, chromium. And then which ligands come first? Anion ligands. Do I have any anion ligands? Chloro. That was an anion ligand. And then I have the neutral ligands in alphabetical order. So neutral ligands, I have amine or ethylene diamine. Which one comes first? En or amine? Well, I would say amine comes before ethylene diamine, right? And so amine comes first, followed by ethylene diamine. And how many ethylene diamines do I have? 2. However, the book is probably going to write ethylene diamine before amine because it's alphabetical according to their formula, N versus E. But you can leave it like this, just so we are consistent. Or you could change it. Now, what's the charge on this cation? So chromium's plus 3, chloride is minus 1, so 3 minus 1 is plus 2. And so they balance out, so I just need 1-to-1 ratio. So 1 of these for every one of those. All right, we'll just do the last one here. We have to move on, otherwise, actually, Tuesday, Wednesday? Farther. This one is a cation, complex cation. Do you see the space here? So this is the cation and then the space anion. And so let's do those. So we got a complex cation over here and a complex anion over here. And so let's go with the cation first. The cation first is tris ethylene diamine iron 3. So what's the formula for that? Fe. Ethylene diamine? En3. No, that was easy. Tris ethylene diamine iron 3. The whole charge on this, ethylene diamines are neutral. So this whole thing will be 3 plus. Okay, let's go to the anion. The anion is going to be hexacyanoferrate 2. So how do we write that out? Fe. Cn 6. Oh, iron's 2. So if iron's 2, this is 2 plus minus 6 gives us 4 minus. Right? And so how many of these do I need? And how many of these do I need? Well, it looks like I need 4 of these and 3 of these to balance out the charge. And so it's going to be Fe En3 sub 4 Fe Cn6 sub 3. And that would be the correct formula for this. All right, any questions on nomenclature and writing formulas?
For thiosulfate, what's the charge on that?
Okay, for thiosulfate, it is, if you take a sulfate like this, SO4 2 minus, and then you decide, I'm going to replace one of these oxygens with a sulfur. If I replace one of these oxygens with a sulfur, actually, let's not replace that one, let's replace this one. Did that change anything? No, because the sulfur and oxygen have the same number of valence electrons. And so it has the same exact charge as sulfate. This would be thiosulfate, replacing one of the oxygens with a sulfur. That's 2O3. Thio compounds are, I used to work with thio compounds, like alcohols. Rather than having an alcohol with oxygen, you have an alcohol with a sulfur. One thing about thio compounds is they smell bad. You know, skunk odors are full of thio, sulfur-containing compounds. Okay, any other questions? Okay. We're going to start our sequence. We're just skipping chapter 15 chapter 14 for right now. We're skipping chapter 14 and moving to chapter 15, Principles of Chemical Equilibrium. Some reactions are lightning bulb. Sometimes when you smell the lightning bolt or whatever else, you can smell ozone, or sometimes you can smell this. This is NO, nitric oxide. The air consists of nitrogen and oxygen. Do you know in what proportions the room air is about, roughly?
12 to 16% oxygen.
Okay, yeah, something like that. I just round it, like 20% oxygen, 80% nitrogen, roughly. But do they react normally with each other? No, they don't normally react. But under these conditions, like if you have lightning bolt, high temperature, high energy, then you can get these to react to form a little bit of NO. But this is not a complete reaction, not all the nitrogen and oxygen, just a little bit react at high temperature. But we want to look at these kind of reactions that, only go a little bit or partially react. This is just a very, very partial reaction. And as long as we maintain that temperature, we'll have a steady amount of product. So what we want to do is we want to look at these types of reactions here. So let me show you something. Okay, if you look at this reaction, 15-1, this is a redox reaction. Copper 2 reacting with tin 2. One of the chemical properties of tin 2 is it's used as a reducer. Tin 2 is a pretty good reducer, meaning even though it's got a 2+ charge, it can lose electrons fairly easily. In this case, copper 2 is going to be the oxidizer. So copper 2 oxidizes tin 2. In the process, copper 2 goes to copper 1, and tin 2 goes to tin 4. Normally if we use the chart method, we would have predicted copper 2 would go to copper metal, and then tin 2 would go to tin 4 using the chart method. But under these conditions, copper 2 only goes to copper 1. It turns out that this reaction does not go to completion. We don't look at the limiting reagent, excess reagent, and then figure out the theoretical yield. What happens here is this is only partial reaction. And so let's look at some of the data on this experiment here. Here's this showing. Why does this not? Well, because a reverse reaction can occur too. And so, if you have forward reaction, what typically happens is the concentration of the products builds up. As the concentration of the products builds up, then the reverse reaction is more likely to happen because there's more collisions. Okay. So this is just showing the reverse reaction. The reverse reaction is copper plus tin 4. We normally don't show the reverse reaction. We normally don't rewrite the reverse reaction. What we normally do is we write 2 arrows, like this, showing that both the forward and the reverse reaction occur. These 2 arrows. That shows an equilibrium type situation or this type of situation. Okay, so we're talking about this reaction, so let's continue on with this particular reaction here. So we do some experiments, 3 experiments here. So we take some copper 2 and tin 2. And then, look at, it's a 2-to-1 ratio, right? 2-to-1 ratio. And so in experiment 1, these are the initial amounts. If you look at the initial amounts, we take 0.100 moles of copper 2 and 0.100 moles of tin 2. Let's do a stoichiometry calculation in our head. What's the limiting reagent? If I have 0.100 moles of copper 2 and 0.100 moles of tin 2, what's my limiting reagent? Copper is the limiting reagent here because I need twice as much. If I have 0.100 moles of tin, I need twice as much copper, which would be 0.200. And so copper is my limiting reagent. That means I should react that completely. And so if I react that completely, this is what it would be using Chem 1A stoichiometry. Let's take a look. And so I'm going to write this table. This is table 15.1. Modify. If we approach this by Chem 1A, this is what we'd have. This is setting up the stoichiometry problem a little differently. This is what we'll call an ICE table or ICE table to do our stoichiometry. So this would be 2 copper 2s plus a tin 2. This is going to yield a 2 copper 1s plus a tin 4. And so initially we have 0.100 moles, and we have 0 moles of product, 0 moles and 0 moles. And then what is the LR? The LR is the copper, so the LR is consumed completely. We will lose all of our LR, right? The limiting reagent. And so we end up with 0 moles of limiting reagent at the end of the reaction, correct? Mm-hmm. And so if we lose 0.100 moles, we're only going to lose half the tin. Does that make sense? Mm-hmm. because, so we're only gonna lose half of that, 0.050 moles, because, in other words, what we do is we call this minus 2x, and therefore this would be minus x, based on the coefficient. This is 2 of x, this is 1 of x. And so, minus 2x is 0.100, therefore x is 0.050, or 0.0500, and this is gonna give us 0.050 moles at the end here. And then over here, this is going to be plus 2x. Well, plus 2x is plus 0.100 here. And so I should end up with 0.100 moles here. And this is plus x. Well, plus x is plus 0.050 or 0.0500 to keep the 6 figs correct. So I'll just call it 0.0500 moles. You see, and then we're done. This is our stoichiometry calculation, Chem 1A, set up in an ICE table. ICE means initial. This is the change. And this is the end, or equilibrium. End of reaction, or equilibrium. And so we expect this to react to completion, right? But that's not what is observed, you know? Did we consume all our limiting reagent? No, we didn't. And what happened is you can let this go on and on and on, but nothing happens. It's stuck. This is the end of the reaction. This is as much reaction as you're going to get. And so we only lost 36% of our, in other words, only 36% of our limiting reagent reacted. 36%. 36%. And so what you should do is you should take a look at these numbers here. We'll talk about them more, but you're trying to find a pattern in those numbers. So we're going to stop here. We'll continue next time.